right, so now we want to explain why we can determine if vectors span a space by finding the determinant of a matrix made by the individual vectors. So let's think about this. If we're trying to determine if vectors span Rn, so that would mean that we're looking for a linear combination. So K1, V1, K2, V2, K3, V3, Kn, Vn, and all of these are vectors and our K values are elements are real. These would have to equal to some point in our Rn. So that would give us, so I'm going to use x1, x2, xn rather than x, y, z because we don't know how many values we're looking at. So if this is true, we can find some linear combination. Well, I could rewrite this addition as thinking about a vector multiplication. So I would have, this is a linear system, so I could rewrite it as my vector v1. So v1, let's say that would be, how do I say this? There would be, let's call it v11, v12, down to v1n, and then v21, v22, down to v2n, etc., down to vn1, down to vnn. And then I would take that and I would multiply it by my coefficients. So I would have my K1, K2, K3, etc., down to my Kn. All right, and then this would be equal to some point in Rn. So if I was going to solve this equation, if there was a solution, that means that I would be looking for my linear combination. So now I've got some vector A times some matrix A times my vector K equal to my solution matrix, which is any random point. So K would be equal to A inverse times X. Well, finding the determinant of A tells me whether or not A inverse exists. So A inverse exists if the determinant of A is not equal to 0. So if I can make my matrix and then determine whether or not the inverse exists, then I know whether or not we span the system. If we're not going to span, it means that our vectors are not linearly independent, and we're going to look at that next.